discriminant function is actually just a rehash of MANOVA. And by a rehash, I mean it's MANOVA, just used in a slightly different way. And we're going to use some of the components of MANOVA that MANOVA tends to gloss over. And I mentioned that before, that when we go back to canonical correlation, you know, it has weights and all these different aspects like loadings and stuff that seem to sort of go away when we go to MANOVA. So when I say that like MANOVA is just a version of canonical correlation, it's sort of hard to see that because all those parts aren't there. There's no loading matrix. We don't talk about weights. There's lots of things we don't talk about in MANOVA that make it seem less familiar. It doesn't seem like canonical correlation at all. And then we're going to talk today about discriminant function analysis, which is going to bring the connection between MANOVA and canonical correlation into into light a little bit more. All right, discriminant function analysis is I think I mentioned this before, and you might recall it. Like it's basically MANOVA in reverse. So what would MANOVA in reverse mean? So who's over there? I see, is that Abby? I know I see your picture up there, but if your microphone is there, what would MANOVA in reverse mean, do you think? Well, think about it. So describe a MANOVA. What do you do with a MANOVA? It can be like general, it doesn't have to be like mathematical. I mean, like when would you use a MANOVA? What would you use it for? And what kind of independent variables are they? Are they groups? Are they continuous? Are they, what kind of independent variables do you usually use? I got you, I'm pressuring you. So if you were to do a MANOVA for your own purposes, what would you use it for? You would want to do what with it? What would be the main hypothesis? Dependent variables should be continuous, and then the independent variables should be just like an ANOVA. Yeah, they should be groups. All right, so you have a bunch of groups, and the main question is: are those groups significantly different on those group of DVs? Right. So what would it mean for that to be in reverse? Same variables, same everything, same setup. It's just instead of saying are these groups different on these continuous variables, how would we say that in reverse? No, I mean that's basically the null hypothesis. But by reverse, I mean treat the DVs now as IVs and the IVs now as DVs. So what would that look like? Right, so the dependent variable is now the grouping. That's right, and the IVs now are the continuous variables that we had as DVs before. So the reason why it's reversed is we're going to try to use the continuous variables that we have that we were treating as DVs in MANOVA. We're going to use them to try to see if we can predict group membership. So an example would be, let's say you give people, some personality measures, and you want to be able to predict whether they're Republican, Democrat, or independent. So MANOVA would say, are Republicans, Democrats, and independents different on these personality measures? That's a sort of MANOVA hypothesis. Discriminant function flips that around and says, okay, well, can we use these personality measures to predict which group someone might be in? Can I predict if someone is a Democrat or Republican or independent based on their responses to these continuous variables? The trick there, though, is that we're not doing anything different or even remotely mathematically different from MANOVA. It's actually the same exact mechanism as MANOVA. We're just going to do a deeper dive into the loadings and other things to figure out exactly how we can use those variables to differentiate people on those groups. And if we can differentiate them, well, then why can't we predict which group they might belong to based on their responses? And then we can also, it adds a little bit of extra work because now we got to look, okay, well, how good a job did we do predicting the group membership? So we can actually look at fit and other things of how well our predictions matched their actual group membership. All right, so let's go further into this sucker. So, like it says here, it's used to predict group membership from a set of continuous predictors. Think of it as MANOVA in reverse. In MANOVA, we asked if groups are significantly different on a set of linearly combined DVs. Now, if this is true, like if we have a significant MANOVA, then we can use those same DVs to predict group membership. So the logic is like this. If I can significantly differentiate between people based on some continuous variables, then why can't I use those continuous variables then to predict which group they might belong to? Because if those groups are so different, then the responses on the linearly combined DVs, the variables, should be able to tell us which group they belong to if they're that differentiated or differentiatable. That's a word. Anyway, so the big question here is, how can continuous variables be linearly combined to best classify a subject into a group? So we're now getting into classification. We're using the mathematics and stuff behind MANOVA to try to classify people. Now, why might we want to classify people? What would be the point of it? I was going to pick on somebody else. Hector. Yeah, why would you want to classify people? If you already know what group they belong to, then why do we want to try to classify them? Yeah, or independent. Like, what would be the point of trying to figure out an equation that would put people into groups? Especially if we already know their group, why do we care about trying to classify them? Of new people, right? Right. Right, now this seems kind of silly. Like a new person comes along and you want to know if they're Republican or Democrat. That's not something that's likely going to happen. But it's possible that you could think of anytime you go on to, I don't know, on the internet, some kind of social media thing. There's all these things like, take this test and it'll tell you what Disney princess you are, or whatever goofy thing that they have on there. Most of them, I think, are like bullshit that they just sort of randomly give you a thing, right? Because my son will, tell me one of these things, and I'm like, do it again, answer the same way, and see if you get the same outcome. And usually he doesn't. It'll just give you some other random, like, which Hogwarts house are you? Those kind of things. Basically, those things are doing like a fake, often a fake discriminant function analysis. Sometimes they're real in terms of the questions. They will classify you based on your responses, and if that's true, then it's basically doing a type of discriminant function analysis. The idea being that if you don't know what somebody actually is, where they actually belong, you actually might be able to classify them pretty accurately. But you have to have a set of people where you know their group membership, and you know how they respond to those questions to sort of set it up first. So discriminant function analysis really helps to sort of set that up. So I'll give you a good example of when that is sort of useful, right? So let's say you go to the doctor and they give you a bunch of tests. You could go for your yearly physical. They test your breathing, or they take blood. So you're looking at whatever white blood cell counts, other stuff that's in your blood. They do all kinds of tests, and they come back, and those tests are put up against a lot of different diagnostic things, right? So if a test comes back and says that you're at risk for whatever, for heart disease or whatever, those things are all types of discriminant function like tests. So they know people who have heart disease take these tests. They're able to differentiate between those and people who don't have it. So that when a new person comes along and takes those same tests, if they end up getting classified as having heart disease, then there's a likelihood, or higher than likely, a higher probability that they actually have it. So it's a way of trying to predict membership for people whose membership you don't actually know. But the first thing is to set up, can we actually do that? Can we actually accurately predict people even when we know their group membership? And then as new people come along, we can actually then predict them pretty well. This also applies to things like graduate school. You're applying to grad schools, and they ask you for your GPA and GRE scores and a bunch of other stuff. They're trying to use a bunch of different predictors to see how well, to be able to predict how well you might do in graduate school. Your chance of success versus failure in graduate school. And presumably that would be done by looking at graduates that, the graduate students they already have, looking at the measures that actually predict those that were successful and those weren't, and actually being able to figure that out. I don't think it actually is done that way most of the time. I think it's just more subjective than it is like some mathematical classification system, but I feel like it should be that way, but I don't think it is. But those are types of things where you might want to use discriminant function analysis. The only trick is the predictors need to be sort of continuous, and you should be able to linearly combine them to make that differentiation. All right. So MANOVA and discriminant function analysis are mathematically identical, but emphasize different things. Discriminant function is usually concerned with actually putting people into groups and actual classification and testing how well or how poorly the subjects are classified. Where MANOVA doesn't do that. MANOVA doesn't care. When you do MANOVA, MANOVA doesn't ask the question of like, well, all right, the groups are different, but how are they different? How are we combining these DVs together? It just is like, as long as you come back with any significant differences in a multivariate test, that's it. That's all MANOVA cares about. We can do it. So now let's move on, and we'll do it as a univariate test to see where the groups actually are different. Discriminant function analysis actually cares about the loadings and the weights and all those things to figure out how those variables are being combined into a meaningful sort of classification. Discriminant is interested in exactly how groups are differentiated, not just that they are different. So MANOVA just says, all right, there's a significant difference someplace. And that's it. The MANOVA test is sort of done. You move on to newer stuff, to basically the univariate test, or to doing like a Roy Bargman or some other kind of process after the significant difference is found. Just like with anything, any kind of regression analysis, you can actually do, you can actually give higher priority or lower priority to different variables in the analysis, and basically do like sequential discriminant functions, or you can even have discriminant function version of sort of a MANOVA, where you're looking at the group differences but controlling for a covariate. So all those things are sort of possible. Anything you can do sort of in a MANOVA situation you can do with discriminant function analysis, but you can also do other things too, like a forward or backward sequential version of it, where you're adding in the continuous predictor sort of one at a time, or in groups or something, to see if they add to the ability to differentiate between groups. The primary goal is to find a dimension or dimensions, oops, sorry, hit the button, that groups are different on, so we can actually put them in, you can classify them. And can group membership be accurately predicted by a set of predictors? It's essentially the same question as MANOVA, just asked a little different. If we can accurately predict groups, then that means groups are differentiated in MANOVA, right? So that if groups are significantly different in MANOVA, then it's likely we can use those weights and loadings to differentiate them and do some kind of prediction. Whether or not it'd be a good prediction in terms of being accurate is debatable, but at least it would be significant. You'd be able to differentiate them in some way. And sometimes your ability to differentiate is not exactly what you want. So go back to the Democrat, Republican, independent. What you might find is that the Democrat, Republican, independent may only be differentiatable on one dimension. And it may come back to like, well, we can tell Republicans from Democrats and independents, but we can't tell independents and Democrats from each other. Right? So depending on how the variables are sort of used, you might not be able to differentiate between all the groups, but maybe just one group from the others. So the other two it's not very good for classifying the other two groups. So essentially you have like Republican and not Republican is essentially what the classification comes down to. But you can't differentiate the two non-Republican groups from each other. So it depends on how how many dimensions there are that are significant, and exactly how they can be combined to predict group membership. That goes to the same question I was talking about, where, okay, well, how many dimensions do groups differ reliably? So to think about it, the more groups you have, the more dimensions you need to differentiate between groups. With so with two groups, you just need one dimension. It just needs to be one difference, one way of differentiating them. With three groups, you have to have at least two. You want to be able to separate the groups out from each other. You got to have at least two different dimensions that are significant and usable in order for that to be meaningful and be able to differentiate between all three groups. For four, you need three dimensions, and so on. You always need sort of one less dimensions than you have number of groups. So each discriminant function is orthogonal to the previous, and the number of dimensions is equal to either the groups minus 1 or p, whichever is smaller. That sound familiar? Either groups minus 1 or p. So you have two sides of an equation, two sides of a discriminant function, where let's see over here on this side, you have what we typically thought of as the sort of this is the dv side, but now it's I'll just call it these are the sort of interval ratio variables on this side that are all sort of feeding into that. These are like our dv's from before. So I call it dv1, dv2, right? And we're trying to maximize the relationship between that and some set of nominal ordinal variables here, where they're all feeding in from different, what before we thought of as IVs, right? And I'm trying to sort of maximize this thing in the middle, right? I'm trying to make this as different as possible. Well, on this side, all I really need is one IV. I don't even need to have multiples. It's just that one IV now is categorical. So if this IV is categorical, just put 1 there. This is a categorical variable here. The number of categories we have here is going to actually be the limiting factor on how many dimensions we have. That's why it says each discriminant function is orthogonal to the previous, and the number of dimensions, the number of times we can actually relate these things, relates to either the number of DVs on this side or the number of groups on this side. So it's either going to be whatever G groups minus 1 or the number of DVs on this side, which is P, right? So it's either going to be P or G minus 1, whichever of those is smaller. Okay? So if I have 2 DVs and 3 groups, it's not going to matter because it's 2 and 2. But if I have 2 DVs and 5 groups, I'm still only going to get 2 dimensions because I only have 2 DVs. If I have 5 DVs but only 2 groups, I'm only going to get 1 dimension because there's 2 groups minus 1, only 1. G minus 1 is just 1. So I can only have one way of differentiating between those 2 groups. So on the 2 sides, I'm either going to have whichever is smaller, number of DVs, which is P, or the groups minus 1, which is just the number of groups minus 1. Oftentimes we refer to this as K minus 1 in like ANOVA and stuff. Questions about that? So you notice the setup, it's the same as if it were MANOVA. Right, same as it was for MANOVA. It's just in MANOVA we were treating this as the IVs and these as the DVs, and now we're just flipping it. I want to use this as these as the predictors, and I'm using this on this side as the outcome measure to see if we actually can predict it. And the best way to differentiate between groups is to try to use these DVs in combination to maximally differentiate between the categories like we do in MANOVA. And if we can do that, then we can use that information then to sort of do some classification. That's a great question. So the question, I'm just repeating it because you can't hear it on the video. The question is, do you need to do MANOVA first to figure out if there's significant group differences before going through and sort of doing classification and doing the rest of the discriminant function analysis? So the short answer is no, you don't. But the longer answer is sort of yes and no. So if you do a MANOVA and and it's significant, and I mentioned this in the MANOVA lecture, that one of the things you can do as like sort of a post-test for MANOVA is to do discriminant function analysis to figure out which DVs are important. So it can be done as a follow-up to MANOVA. But if the goal is discriminant function analysis, like the goal is classification, then it's going to give you tests, the same test that you get in MANOVA, you're going to get in discriminant function analysis, plus all the rest of the information that discriminant function analysis provides you without having to do both. Right? It'll sort of do discriminant function analysis, basically doing both of them at the same time. Right? So a lot of people do discriminant function analysis as a follow-up to MANOVA, but it doesn't have to be done that way. If the goal is discriminant function analysis, you can just go straight to it. You'll get all those tests like Pillai's trace and Wilks lambda, all those tests are going to come back anyway, tell you if it's significant or not. Plus you get a bunch of other information that if you're doing a MANOVA, you don't want. It's actually a lot of noise that would might make it actually more complicated. But if you're trying to classify, you actually do want, because now you're trying to interpret exactly how the groups are being differentiated and how you can actually put people into different groups, classify them, and how good a job that's doing. All right. So are discriminant functions interpretable or meaningful? So as you're going to try to figure out exactly how the groups are being differentiated on these continuous variables, you want to know, all right, well, is it really, is it easy to interpret? Can we figure out? Because sometimes it's difficult, as we saw with like canonical correlation. Sometimes looking at the loadings and trying to figure out exactly what's going on can be sort of difficult, right? It's so funny. I've been looking over there, and there's one of the videos that from here. I can't read the name. I just saw it's like there's like just a square with like light in it, and I'm like, why is nobody there? It's weird. No one's. And I realized it's my own. It's my own feed from back here. Like I'm literally looking. It's this that. Like, why is nobody there? That's really weird. I thought it was strange. Someone put their video on and left. Anyway, sorry, I'm easily distractible this morning. Okay, so you know, we're going to need to go and sort of interpret exactly how these variables are being combined together to differentiate between the groups, and we can then figure out how, you know, do these discriminant functions correlate with each predictor, which is basically looking at the loadings. Can we actually look at the loadings and figure out exactly which variables are important? So another way of saying all this stuff that sounds crazy, if I'm going to a doctor and I want to know, you know, different health outcomes, heart disease and cholesterol and whatever things I'm worried about sort of health-wise, for each kind of test, each kind of differentiation between whether or not you have heart disease or not, or if you have cancer or not, or whatever classification you're trying to look at, different kinds of tests are going to be more important in trying to differentiate those categories. So when it's asking how do the discriminant functions correlate with each predictor, we're trying to figure out, all right, as we're classifying these different groups, which of those predictors, the continuous predictors, seem to be most important in classifying people into each of the different categories. So if you're looking at sort of heart disease versus no heart disease or something, different tests may be important than trying to differentiate between, say, cancer and heart disease, or cancer and health, or whatever. So different types of tests are going to be more important, and those weights are going to come up with, or I should say the loadings are going to show up in those different dimensions as you're trying to differentiate between those groups. All right. And then here's usually the sort of goal is you're trying to set this whole thing up so you can actually classify new unclassified subjects. So you have a bunch of people in which you know their group membership, and you're trying to figure out if we can actually predict it accurately. And then once you actually establish that there is a pretty good prediction, you can actually get them classified pretty well, and there's a pretty good fit of people's actual classification to their predicted classification. You can then go through and classify people as new people as they come in when you don't know their group membership, and be able to sort of make predictions about where they should be in terms of what groups and stuff like that. And then we look at strength of association the same way we would with MANOVA. We can see if look at R squared or eta squared, those kinds of things, to see how highly they are related to one another. I sort of already said that before, but which predictors are more important in predicting group membership? Can we predict group membership after removing the effects of one or more covariates? So we put covariates in there to try to reduce noise, to try to bring down some of the variability that's going to make it harder to predict. And if we actually remove that error variability, can we then do a better job of predicting group membership? Because maybe that noise is making it difficult. And then, of course, there's always can we predict population parameters sort of outside or beyond the sample that we're using. So what are the assumptions? Well, the assumptions are the same, because since we're using MANOVA, it's the same thing. So usually discriminant is used with existing groups. So if classification is your goal, you don't really care about the assumptions as long as the classification is good. So so think about that for a second. If my goal is wanting to accurately classify people, and I do MANOVA and I've violated every assumption, right? So normality is violated, there's outliers, there's, I mean, all kinds, it's just messy as hell. And you get all kinds of problems with MANOVA, but you don't really care about the significance. You want it to be significant, but you don't really care about it as much as the classification. Then you can pretty much ignore violating every assumption as long as the classification actually does a good job. Because that's all you really care about. If it's actually accurately predicting people into their groups, I don't care how it got there. I don't care what corners I had to cut or whatever. It doesn't matter. As long as it's doing a good job, the assumptions really don't make a difference. If you're doing something with random assignment, this would be a little strange, like you're doing an experiment and you have different experimental treatment groups and like a control or something, and you're trying to predict which group someone might belong to, which would be an odd way. You could do that, which would be the same as doing MANOVA. And then you can actually make some causal inferences and stuff if you really wanted to, but that's be a strange use of discriminant function analysis. Usually they're used with pre-existing sort of groups or categories more commonly, but I guess if you really, really wanted to, you could. Or if you did a MANOVA and you wanted to know, how the DVs are sort of contributing to it, you can do a discriminant function afterwards, and you might be able to make some causal inferences about that. But the main thing here is that if really you're just trying to classify people, the accuracy of the classification really is more important. The assumptions probably don't matter so much. However, that being said, if the assumptions are met, your chances of actually accurately predicting group membership are probably going to be higher. Right? You can have a better chance of it if you actually meet all the assumptions. Because the assumptions, if you violate them, there's a chance it's going to lower power. You're going to have issues like if you violate the homogeneity covariance matrices assumption, it's likely your power is actually going to be lower. So your ability to differentiate between groups is going to be lower. So even though I'm saying this, it doesn't matter as long as it's accurate. Meeting the assumptions will likely make it more accurate. So the assumptions are exactly the same as are for MANOVA. I can't stress this enough. It's the same thing as MANOVA. MANOVA, it's the same process. So we're still assuming linearity and normality and all that stuff. The homogeneity of covariance matrices is still the sort of major, assumption we have that's a little different than, say, an ANOVA. But pretty much all the same assumptions. Everything's the same. All right. So classification's goal, the analysis is highly influenced by violations of homogeneity of variance covariance matrices, because subjects will tend to be classified in groups with larger dispersion. So if you have a group that has more variability in it, it's actually going to get sort of weighted more in the classification process. So you're likely to be misclassifying people into that group. And also, it doesn't say it here. If you have drastically unequal n, or you say like one group is 60% versus 40%, or even let's say it's even more drastic, 80% versus 20% of your overall sample split into those two groups. Like 80% of your sample are Republicans and 20% are Democrats. You're likely going to overestimate or overclassify everyone into Republican, because it's hard to beat 80% correct. Meaning that if I was just to predict that everyone's Republican, I'd be right 80% of the time. It's going to be difficult to do better than 80%. So you're only going to be able to incrementally get better by classifying people into Democrat. So large group differences will also make a big difference, especially if they also come with, if the larger groups also have larger variability. You're going to be misclassifying a lot of people into that group, because they're going to be sort of drawn into that larger sample size and larger dispersion. Anyway, so you can look at this by plotting discriminant function scores for at least the first two functions and comparing them to see if the spread is about the same size. We'll talk about that a little later. If violated, you can always transform the data. And you can actually use separate matrices during classification. There's quadratic discriminant functions, all kinds of other crazy stuff. There's even like non-parametric classification functions you can use. You can switch to logistic regression, which we're going to talk about next anyway. So there's other ways around it if you're having issues with the assumptions or something in discriminant function analysis. So when looking at this first part, significance of the overall analysis, do the predictors separate the groups? This is the same thing. Like this is literally like this says like MANOVA review. That's a horrible color. Holy crap, that's bad. Can you actually see that or read the numbers? I can't. I literally gotta like look super close to even see it. All right, so there's memory, perception, communication. So these two different groups, I think these are different problems. So they have like a performance scale, an information scale, which I think is sort of like another version of sort of memory scale, verbal expression, and you have the person's age. And they're using those to see if they can combine these together somehow to predict whether or not someone has a memory issue, a perception issue, or a communication issue. And basically what we want, these S's represent those S matrices. This is like the sum of squares and cross product matrix total, sum of squares cross product matrix between groups, and the sum of squares and cross products matrix for within groups. So anyway, what I'm saying here is that the good news is this part is just MANOVA. It's exactly MANOVA. I don't mean it's sort of like MANOVA. I mean it is MANOVA. All right, we're doing the exact same process. I'm going to go through this kind of fast. We take these four DVs, and we want to be able to sort of combine them to see if these groups are different. And we do that by creating all these matrices. So we have the sum of squares and cross product matrix for between groups. How do we get those? Going back again. This first person, all right, we can actually take and average the people in the first group, like this 87, 97, 112, like all their scores all the way down. Take the people in the first group and get their averages. The people in the second group get their averages. People in the third group get their averages, and actually look at those averages relative to the grand mean. So and do that for each person. All right, so remember those. For like the S between groups matrix, we're going to take n times, and we're going to sum up all these different. How do I make sure I do this as a matrix? So we're going to take these are like the vector of means for each group, making that so it's like it's a vector of the means. So each group means because you have four of them, there can be four group means for group one. And I subtract out the sort of vector of the grand means, which there'll be four of them as well. And we're going to multiply that by what? Anybody remember? No one remembers? How do you square matrices? Yeah. So then I'm going to multiply this. Let's write that in by the transpose of the exact same difference. I'm trying to stress that these are matrices. That's why I'm overemphasizing the capital. But I'm going to multiply that by the transpose. That's going to give me an S matrix between groups. So for the first group, I'm going to take the first group's four means minus the four grand means. Right? So I'm going to have a vector of differences. I'm going to multiply that by the transpose of the same differences. And I'm going to get, in this case, because there's four means, the S between groups matrix is going to be a 4 by 4 matrix. Right? You're going to have a 4 by 4 matrix of sum of squares and cross products that you're going to have for group number 1. You can do it for group number 2 and group number 3. You're going to add them all together, and you're going to multiply by n. Right, does this sound familiar? So we did the same thing in MANOVA. It's just the matrix version of doing sum of squares. We're just getting sum of squares and cross products. So this is, again, 4 group means from group 1 minus the 4 grand means times this transpose. 4 group means from group 2 minus the grand means, right, times this transpose. The 4 group means from group 3 minus the grand means times this transpose. So I'm going to have 3 different matrices, 1 for each group. I'm going to add them up. And then I'll multiply by n to get this group, the sum of squares and cross product matrix that's on the top here. right? So I mean, I'm sort of doing this as a review, but this is sort of what we talked about in MANOVA. So we get the sum of squares are going down the diagonal like that. The off diagonals are the cross products, and those were summed together from all the three different groups. Erase this. To actually get the sum of squares and cross products matrix for between groups, which we call the S matrix. Okay, S between groups. So here's the question: how do I go about getting the within groups? By the way, do you need me to talk more about the between groups first before we go on to talk about within groups? Because let's make sure we're all clear on that. So, we're clear on how do we get the S between groups matrix? So like if I asked you to do that with the numbers that are here, could you do that? Not for each person, but for each group, because it's between groups, right? So I'm gonna get in the sense that maybe here, let's do something here. Can I, if I go to, let's go here real fast. You guys can all see this, right? Next, opening Excel, you can see that. All right. So for a second, let's think about these numbers. Let me get rid of this. Okay, so what are the numbers here? So 87, 5, 31, 6.4. So tell me what the numbers are. 97, 7, 36. Those are tiny on my screen. 8.3. What's next? Okay. Keep going. Okay. 85. Oops. 10. Keep going. Okay. All right. Okay. Oops. Okay. Okay. So if I wanted to do this, so this is now the. Let me put this all the way open. So this is now memory, I think. This is perception. And this is communication, if I remember correctly. And then these I don't remember. Perf info. Verb expression and age, right? Okay. So those now, so if I wanted to do between groups, I want to figure out the S matrix for between groups, what do I need? What's the first thing I need to do? I'll pick on Devere, just because you're the first person I saw left over there. What's missing? Yeah, so because the way this is set up, I can't really do the sum of squares and cross products for for between groups, because I don't have the information I need. So based on the equation I was talking about a second ago, what do I need to do the between groups sum of squares and cross products matrix? So not a cross. I mean, it depends on what you mean by a cross, but I think you're at the right idea. So let's say these are the means, right? So there's the average for that. For all four of those. You do the same thing for those, same thing for those. And we also need the grand mean. I'll put those down here just to make sure they're different. It's actually now it's the grand means, which seems weird, but it is what it is. Equals average of these, those. Okay, so there are the grand means for those. So to do the sum of squares and cross products matrix, so I know that each one of these represents 3 people, so my n is going to be 3. I need to be able to do this for each group. So I need to be able to take and subtract these means from these means, right? So to do that, I'm going to, just for a second, I want to transpose these. I'm going to, let's see, be special. I need just the values and I want to transpose them like that. Okay. So there's those 4 means. I'm going to do the same thing with the grand means. Oops. Right, so there's those grand means. I'm just going to literally just subtract each of those scores, the corresponding scores from one another. Oops. And get a difference. Okay, so here's my 4 by 1 vector. All right, so when thinking about it, let me switch back over to here for a second. I'm actually going to put this. All right, so in doing those, we had, like I did a second ago, we got n times the sum of this x. This is really like with a bar over it, j, the means of the group minus the grand means, right? And I'm multiplying that by its transpose. And again, these are means. These also means. Its transpose. And I should, in the end, get a 4 by 4 matrix, right? So I'm doing this for group 1, group number 1. All right, let me switch back. I'm going to take, so here, this is the x minus y, right? So here's x, the x bars. I'll just call them x bars, minus the y, gm. Right? Those are those 2 vectors. I subtracted them, and this is the result. This is the x bars minus the y. Sure, there should be gm's. These are all grand means, right? So this is for just group 1. The y1, the x1 bars minus the y grand means. With me so far? So now I need to multiply this by its transpose. So I need to actually put the transpose in here. Again, values, transpose, okay. So there's my transposed matrix. So it's this. Transposed. All right, and if I multiply those, I should get a 1, 2, 3, 4 by 1, 2, 3, 4 matrix. If I do it right, equals M mult, that's matrix multiplication, array 1, array 2, I use Control Shift and Enter, it gives me, this is my group 1 deviations. Okay, so far so good. Now I really should either multiply by n now, or I can add them together and multiply by n. But essentially, that's just for group 1. I need to do the same thing for group 2, the same thing for group 3, same thing for group 4. I need to do, so I can do that for each of these. Let's see, put it here, put it again here, put this transposed. So I should be able to then copy the rest of this, I think. Let's see if I'm right. And then if I were to equals add, what am I doing? There's no add. Just say I want this, oops, this plus that, all multiplied by 3. No, we're just getting too huge. I think I'm doing something goofy. Why are these numbers getting so small? This, oh, because it's tiny because of the negatives. This shouldn't. This. Hold on 1 second. I think I need to redo this. Hold on 1 second. Nope, same. Am I doing something goofy? Let's see. These those are all subtracting, that's right. Should be able to just add those up. It's because they're tiny little numbers. A lot of these. That plus, why am I getting zeros? Yeah, it just happens to be exactly the same across all of them. So this is the different matrices for each of the different groups. This times transpose Should be that. And within say one more time. Mm-hmm. 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 Ah, thank you. That's what the problem is. Thank you so much. That's looking at. All right, sweet. That's why none of this is making any damn sense. Okay, here we go. Okay, now let's go back over here. Now this is making more sense, I think. Thank God. All right. For a second, I thought we were going to be normal. It was like, well, I don't know. Let's just move on anyway. All right, perfect. That. So this should be then our S between groups. Should equals that. Not that. Okay, so this is our S matrix. So we did that for each group. Make sense? Each group means minus the grand means times this transpose, and we add them all up and multiply by 3 to get the matrix that is in here, hopefully, this matrix. So how do we get the within groups matrix? I'm not going to do it because it'll take forever. But how do we apply this to the within groups matrix? And copy this back over again. Over here. Well, how do we go about doing that? Right. So when so if you think about total, all right, let's go. That's another easy one. This is now all the group means around the grand mean. That's the same thing it was when it was a univariate. Each group mean around the grand mean is between groups. Total would be each person's score around the grand means. So it'd be the same process here, subtracting the grand means, but I'd be doing it for every person, taking these 4 scores for the person number 1, right? And I would subtract out, instead of subtracting out, the group means and the grand means, I'm going to take and subtract out for like total, right? It would be subtracting out the, go back over here and grab these because it's easier, it's already transposed. I'd be subtracting out the grand means, right? So person number 1, take their scores, subtract out the grand mean, and we get a difference. I'm going to multiply that by this transpose. All right. And then I'm going to get for each person, now there's going to be each person is going to have a matrix that is the difference between their scores and the grand mean for total. How would I do it differently if it's within groups? I still got to do it for each person. Within groups is generally each person's score. Go back to here. And let's do that again. Now we're talking about for the S within groups. I'm not going to do all of it because it would take us forever. I'm now taking each person's individual score in each group. It's their vector of scores. That's why I'm drawing it with a funny X. Minus the mean for each group, or the means vector of means for each group, and I'm going to multiply that by its transpose. Again, each individual score on X. Again, it's a vector of scores for each individual in group J, minus the means group J, its transpose. So instead of taking, like with total, instead of taking and subtracting the grand means, I'm going to take and subtract out these group means. So these are the group means for group 1. Right? So this is the group means for group 1 are just 98.677, 36.333, and 7.3. So I was taking the person number 1 score. So this is, X1. This is the X1 means, X bars, right? This is now the difference between those. I gotta then multiply this by its transpose. And in fact, what I should have done is I just transpose it and leave the scores alone. It probably would work. Actually, no, it won't. I lied. Why won't you work, dummy? Yeah, that's for a second. No, it won't work, I guess. Fine. So this now is person number 1's, sort of contribution to the S within groups matrix. I would need to do the same thing for person number 2 versus the group means. Person number 3 versus the group means. And then I would switch to person number 4 minus these group means. Person 5 versus these group means. Person 6 versus the same group 2 means. And then I would switch to group 3 and do person 7 versus these group means. Person 8 versus these group means. Person 9 versus these group means. So I would have 9 individual matrices, 9 4x4 matrices for each person, not 9 for each person, but 9, 1 for each person. And then I would add up all 9 of those matrices. You add up all those matrices and you get an S within groups matrix. Okay? Does that help make that clearer than it was before, I hope? Okay, exactly how those matrices are put together. All right. We're running out of time, so I gotta get moving. So here are those. Again, this is like my cooking show analogy. Here's the cake already in the oven. Right? They're already completed, already sort of done, and we've already sort of added up all those pieces to make the within groups and between groups matrices. And once I have those, I can then figure out if there's an overall significance for the discriminant function. Basically just do like we do with MANOVA. Use these matrices, the between groups S matrix and within groups S matrix, to find, because remember the lambda is shown down here, is the S within group, the determinant of the S within groups matrix over, we add together the between and within groups matrices, and we find the determinant of that to get our lambda value, which in this case is 0.010477. So this is the same process it was with MANOVA. We found these matrices, took the error matrix over the effect plus error, and found the determinants of those, and the ratio of those determinants was the lambda value, which we could then plug into this crazy mess to get an F value. So this sounds familiar. You had something like this on the exam, right? Like how to plug this stuff in, find the degrees of freedom, and use the lambda value to come up with an approximate F value that we can use then to see if it's significant. Right? So there's nothing new. we're doing all the same stuff. This is the test for significance. So the significance test in discriminant function analysis is just a MANOVA. Same thing. Okay, questions? Anything we just talked about? Because then we just ran through a bunch of stuff. All right, that's what I want to talk about. So, what starts to differ, and we'll talk about this more next time, is assessing individual dimensions. So with MANOVA, pretty much we got to here, and if this was significant or not, the multivariate part of this was done. We said, all right, there's either a significant multivariate effect or there isn't. If there wasn't an effect, they were just done. That's sort of the true here with discriminant function. If this comes back as not significant, we just, go take a nap or whatever else we do during quarantine, right? We just, watch another episode of Tiger King, something, right? Because this is done. We don't need to do this anymore. But if it's significant, with MANOVA, the general, approach is to then just switch to looking at the ANOVAs, right? One for each DV. With discriminant function analysis, though, the fun is just sort of beginning. We can actually use what we learn in canonical correlation to actually try to then start to interpret the loadings and figure out, okay, well, which variables are actually more or less important when looking at the significant differences. So instead of just like lumping all the dimensions together that MANOVA does and just says, all right, are any of them significant? Discriminant function analysis actually wants to know, okay, well, which dimensions are significant? Just the first one, the first two, the first three? And of those different dimensions that are significant, how are they actually being combined to differentiate between the groups? Said that already. The overall analysis is significant, then most likely at least the first function will be significant, just like with canonical correlation, right? If you get significance anywhere, it's at least going to be the first one because that's the largest dimension. And once the discriminant functions are calculated, each subject is given a discriminant function score. Sound familiar? Like a canonical variance score. It's the same stuff. These scores are then used to calculate correlations between the entries and the discriminant scores. These are called loadings. This is all just rehashing sort of a combination of MANOVA and canonical correlation. Matter of fact, what they call discriminant functions, discriminant function 1, discriminant function 2. In canonical correlation, we just call that canonical correlation 1, canonical correlation 2. They're the same things. We're finding these dimensions and then using them to see exactly how the groups can be differentiated by those continuous variables. All right, so we're not gonna, let's stop here. This will be the first, the first slide next time will be this one. So on number 20, which I think gets us about halfway through, which is good.